This is the next video in the series on section 8.3. This video will cover graphing logarithms. So what we're asked to do, or what you will be asked in this video to examine, is how to graph equations like log base b of x is equal to y, where we have our x and y variables unknown. It turns out there's a nice three-step process for doing this, and we're just not going to pick any values of x. We're going to pick special values of x. So the first step, when I said we're going to look for special values, this is what the whole first step is. What we're going to do is we're going to look for values of x here that are powers of our base b. So we're going to look at this value here, our value x, and choose our values based on our b value. And we're just look at powers of b. So when I say powers of b, we're really going to look at like b to the first, b squared, b cubed, and so on. And we could even go in the negative direction, b to the negative 1, b to the negative 2 power. We could even go b to the 0th. And there's just an infinite number of possibilities that we can choose. So we're just going to look for values of x here that are powers of the base b, and we're going to create a little table, a table of values, sort of like we did when we graphed exponential equations, or exponential functions, that is. We looked for nice values of x and found a value y. In this case, our value of x, our nice values of x, are just these powers of our base b here. Second step for graphing logarithms is we're going to actually evaluate log base b of x to find y. Remember, our x values are just our powers of b, so it should be kind of trivial or easy to find our values of y, since our values of x are powers of b, or powers of the base b. Third step that we have is to just plot all the points and draw the graph. So the points we had, or the table of values we had, are x and y. We'll just go ahead and plot those points that we have found. Remember, our x values are our powers of b, and then our y values are what we did, are the values after we evaluated log base b of x at each x value. And you'll see the process in more depth during the first example or two, and then we'll get a little bit more complicated. Last little bit of terminology before we do an example is a vertical asymptote. We have to discuss what it is to be a vertical asymptote. And all a vertical asymptote is, it's a line the graph of the function approaches as y grows to infinity. So like we had at horizontal asymptotes, being a line that the graph of the function approaches as x goes to infinity, and it's going to be a horizontal line. Same thing's going to happen with vertical asymptotes. It's going to be a line that the graph of the function approaches as y grows to infinity. So as y gets bigger and bigger, then the graph is going to approach some sort of set value for x. Alright, so our first example here is graph log base 3 of x equals y. So by the first step that we have, we're looking for values of x that are powers of our base 3. So in that case, we'd have powers of 3 for x would be 1/9, because that's 3 to the negative set 2 power, 1/3, just 3 to the negative first power, 1, which is 3 to the 0th power, 3, which is 3 to the first power, and 9, which is 3 squared. So when we take it and evaluate, log base 3 of 3 of negative 2, and if you want to remember that logarithms and exponential functions are inverses of each other, you can certainly cancel out the log in the 3 here, just to get a value of negative 2. Remember that property is log base b of b to the x will give you x, and b to the log base b of x gives you x. Those are the two function compositions that are at work behind this. In this case, we have this function composition here of inverses giving us our -2. The 3 and the 3 here would cancel, the logarithm and exponential would cancel to give us our -2. Likewise would happen for log base 3 of 3 to the negative first power will give us a -1. Log base 3 of 3 to the 0 will give us 0. Log base 3 of 3 will give us a 1. And log base 3 of 9 will give us a 2. Because 9 here, you could really rewrite 9 as 3 squared. So now we have the points. So here are the points we have. We have 1/9, -2, 1/3, -1, 1, 0, 3, 1, and 9, 2. And now we can go ahead and graph those points that we've generated using our table here, x and y. So you have 1/9, -2, right around there. 1/3, -1, right around there. 1, 0, 3, 1, and 9, 2, 3, 6, 9, 2, right about there. And now we can connect the dots and draw our graph. Just like that. Now it's important to note here, there is a vertical asymptote because as the graph approaches from the left, from the right, it looks like y grows in the negative y direction, right? So it comes down and it sort of looks like it levels out at the line x is equal to 0. It sort of looks like it levels out. Right here at that line, x is equal to 0, right? That's what the vertical asymptote is. It's that what that line does, or what the graph does, when it levels out, or appears to level out at that line, vertical line, x is equal to 0. So in that case, our vertical asymptote is x is equal to 0. So let's just recap what we did. First thing we did is we found values of x that were powers of our base b here. So we did 1/9 is 3 to the -2 power, 1/3, 3 to the -1, 1, 3, 0, and evaluated log base 3 of all these values to find our y values, -2, -1, 0, 1, and 2. And then all we did was we used those as ordered pairs or coordinates, plotted them, drew the curve, drew the graph, and then denoted the vertical asymptote. So now let's graph log base 1/2 of x equals y. So what we're going to do is we're going to choose, by our first step, we're going to choose values of x that are powers of our base, which is 1/2 in this case. And in this case, our values of x, we get 4, which is equal to 1/2 to the -2. We could pick 8, which is 1/2 to the -3rd power. 2, which is 1/2 to the -1st power. 1, which is 1/2 to the 0th power. 1/2, which is 1/2 to the 1st power. 1/4, which is 1/2 squared. We could keep going if we want. I think that's sufficient enough to see what's going on. So then when we evaluate them, we take log base 1/2 of 4. Remember, 4 is really 1/2 to the negative 2 power. We get out a negative 2. Likewise for 8, you get log base 1/2 of 1/2 to the negative 3rd power. The log and the exponential function part would cancel, giving us a negative 3. And likewise for log base 1/2 of 2 would give us a negative 1. Log base 1/2 of 1 gives us 0. Log base 1/2 of 1/2 gives us 1. Log base 1/2 of 1/4 would give us 2. So there's our points here. We got the points 8, negative 3, 4, negative 2, 2, negative 1, 1, 0, 1/2, 1, 1/4, 2, and so on. So now we can just take these points and graph them. I'll go 1, 0 first, 2, negative 1, 4, negative 2, and 8, negative 3, and 1/2, 1, 1/4, 2, and then I could draw our curve, just like that. So there's what the graph looks like of log base 1/2 of x is equal to y. But there's one part that we can't forget, and that's where the vertical asymptote is. And in this case, as y grows in the positive y direction, it looks like it'll level out at x is equal to 0. So our horizontal asymptote, or vertical asymptote, is the line x is equal to 0. Right. So let's talk about graphing logarithms, but in a different sense, in the fact that we're now going to translate these logarithmic functions, the graphs of them, horizontally and vertically. So, as we've done with exponential functions and radical functions, the process is going to be the same. The graph of log base b of x plus h, notice the x plus h is in parentheses. That denotes order of operations. So the graph of log base b of x plus h plus k equals y will shift or translate the graph of log base b of x equals y by the following units. Negative h units horizontally, and k units vertically. So same as exponentials and radical functions, the graph of log base b of x plus h plus k equals y just shifts log base b of x equals y, negative h units horizontally and k units vertically. That's important to understand here when you're trying to evaluate something like log base b of x plus h plus k. It's important that you do the following when you try and get a value here. You take whatever's in the parentheses first, and you find out what value that is, whatever the x plus h value is. Once you find that, then you can take the logarithm with base b of that value and get some value, and then add k. For our purposes, we're not really going to be doing that, but that's what you would do when you would apply the order of operations to, if you're going to actually try and find what y actually is. But for our purposes, we're going to go ahead and graph log base b of x equals y, the quote parent function, and just shift it, negative h units horizontally and k units vertically, to satisfy what the rule will be for our function, or the whatever logarithmic function we're asked to graph. So first example here of graphing these logarithms using translations. We're asked to graph log base 3 of x minus 2 in parentheses equals y. What we're going to do is we're going to start by graphing the quote-unquote parent function log base 3 of x equals y. And here are the coordinates or ordered pairs that we will graph for log base 3 of x equals y. We have 1, 0, 3, 1, 9, 2. We also have the points below the x-axis set 1/3, -1, 1/9, -2. And we could draw the curve just like such. And then for that one, the vertical asymptote will be at y is equal to 0. So now all that we're going to be doing now with log base 3 of x minus 2 is we're going to shift it negative h units. Remember that negative 2 is the h value. So when we shift it in negative h, we're going to shift it negative 2 units because our h value is negative 2. So when we take negative h, we're going to get a positive 2. So all these points that we graphed here for log base 3 of x equals y, we're just going to shift them to the right 2 units. Just like that. And now we're going to graph it. Just like that. Now, since we moved the graph of log base 3 of x equals y to the right 2 units by our function rule, the vertical asymptote will also move with it. And the vertical asymptote will shift over to the right 2 units as well, or negative h units as well. So our new vertical asymptote will be y is equal to 2. So, just to recap, we were asked to graph log base 3 of x minus 2 in parentheses equals y. To do so, we graphed log base 3 of x equals y first, using the table of values that we know for that graph. And we graphed it using the green marker, and that denoted log base 3 of x equals y. And then we just translated this graph 2 units to the right because of that's what we want to do. We want to shift it to the right 2 units. So took all the points and shifted them to the right 2 units and drew that curve with the blue marker. And then since the asymptote was at y equals 0, that will also move with the horizontal shift as well. So that's why the vertical asymptote is at y is equal to 2. So last example, we're asked to graph log base 1/2 of x plus 3 is equal to y. Now our last example was a horizontal translation, so naturally the next example, this one here, will be a vertical translation. So what we're going to do, I took the liberty of graphing log base 1/2 of x equals y using the table of values that we know of, which are 8, -3, 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 1. If you want to take the time and evaluate log base 1/2 of all these x values, those are the y values that you would receive. So now by what we know about translations, horizontal shift our graph over negative h units, but that's only if we have parentheses involved. We don't have parentheses involved here, so it has to be a vertical shift. So we're just going to shift it up k units. In this case, our k value is 3. So we're going to shift the graph of log base 1/2 of x equals y. All those points are going to move up 3 units, and we will get the following graph. Up 3 units, up 3 units. And up 3 units. So in recap, all we did is took the graph of log base 1/2 of x equals y, graphed it, which is our green graph here, and moved it up 3 units because that's what we were asked to graph. So the line, the graph in blue here represents what we were asked to graph, the vertical shift. And since we didn't really do a horizontal shift, there's no need to move the vertical asymptote, so the vertical asymptote will stay exactly at x is equal to 0. If there were a horizontal shift, then our vertical asymptote would change depending on on wherever our horizontal shift was. But there is none in this example, so our vertical asymptote will just stay at x is equal to 0.